Today's tutorial is going to be about robot kinematics. Basically, it's about being able to coordinate arms or legs of robots. So I have myself here a little quadruped, 4 legs. Each leg has 3 joints, one here, and one here. Now, you would think to be able to place that foot anywhere you want would be quite easy. If you want to move it in and out, you just move that motor. If you want to move it up and down, you just move that motor. If you want to move it forward or backwards, you just move that motor. But unfortunately, that has a bit of a problem with it, as you can see here. When we move that motor, instead of moving the foot in or out, it actually moves the foot in an arc. When we try to pick him up and down with that motor, same thing, it moves it in an arc. And then if we want to walk by pulling our foot forwards or backwards, we move that one, instead of pulling it forwards and backwards, again, it moves it in an arc. So what we need to do is we need to be able to coordinate 2 motors at once, or 3 motors at once sometimes. You can see that gives us a nice straight line by coordinating 2 motors at once. If you want to go up and down, we can do the same thing like that. And more importantly, for walking, you actually need to coordinate 3 motors. And that gets the foot moving in a beautiful straight line. So what we need to do is we need to write ourselves some algorithms that we can just tell the algorithm the x, y, z coordinate we want the foot to be, and that algorithm will work out what degrees to set each one of the 3 motors and set each one of those 3 motors placing the foot exactly where we want. Okay, first let's get some coordinate systems down. I say when the foot is moving in and out from the body, I'll call that the x direction. When it's moving forward or backwards, I call that the y direction. And when it moves up or down, I call that the z direction. For the moment, we're just going to pretend it doesn't have this motor, and this foot can only move up and down or in and out, and we'll calculate those two, and in the next video, I'll show you how to work out that last one. Right, so I've drawn this up here. We have our arm 1 and our arm 2. We want to know what angle to pick up the arm 1, what angle to bring back the arm 2 to give us this x, z placing of this foot. Right, so what I've done is I've drawn in a hypotenuse down there that I've called L. I've drawn down a tangent off the joint till it's right angle with the hypotenuse, right? And I've called from the motor there to that right angle tangent T1, from the right angle tangent to the foot T2, and from the right angle tangent up to that joint there T3. So T1, T2, T3, arm 1, arm 2, hypotenuse L, and of course the x, z coordinates we want to place the foot. Alright, so what we're after is theta 4. Now we do know that theta 4 plus theta 5 will be equal to theta 6. So I've wrote that down. Theta 4 plus theta 5 equals theta 6. We're trying to find what theta 4 is, so we know that theta 4 will be equal to theta 6 plus theta 5. If we can work out theta 6 and theta 5, we know what theta 4 is. Now, we know that that horizontal line and that horizontal line there are parallel, so whatever angle that is, that's the same angle down there, so it'll be theta 5. And we know tan theta 5 will be equal to z over x, opposite over adjacent. So we can write that down. Tan theta 5 equals z over x. Therefore, theta 5 will be equal the inverse tan of z over x. We know what z is, we know what x is, so we can actually calculate theta 5 right now. Right, so working out theta 6. We know that the cos of theta 6 will be equal to adjacent over hypotenuse. So theta 6 equals T1 over A1. Writing that down there. Therefore, theta 6 is equal to the inverse cos of T1 over A1. So now we know how to calculate theta 5, theta 6. We can work out theta 4. So theta 4 will be equal to inverse cos of T1 over A1 minus inverse tan of z over x. Of course, we know what that is. We can calculate that out. We know what A1 is. It's the length of my first arm, but we don't know what T1 is just yet. So we can't quite solve theta 4 till after we have T1. Now for our other angle up here, theta 3, we know theta 3 is equal to theta 1 plus theta 2. So if we can work out theta 1 and we can work out theta 2, we can add the two together and get theta 3. Now we know that the sine of theta 1 is opposite over hypotenuse. We can say the sine of theta 1 equals T1 over A1. We can say that the sine of theta 2 is equal to T2 over A2. I've wrote both those down here. Right? Therefore, theta 1 is the inverse sine of T1 over A1. Theta 2 is the inverse sine of T2 over A2. So if we want to work out theta 3, is adding those two together, those two is equal to that, we can end up with theta 3 equals the inverse sine of T1 over A1 plus the inverse sine of T2 over A2. Of course, we know A1 and we know A2, the length of our arms, but we don't know T1 or T2. So to solve both these angles, we need to know what T1 is and we need to know what T2 is. Right. So looking at a few things we know. We know that T1 plus T2 is equal to L, the length of the whole side there. We can write that down. T1 plus T2 equals L. Therefore, T2 will be equal to L minus T1. We also know that Pythagoras rule, T2 squared plus T3 squared is equal to A squared, written down there. Therefore, T2 squared is equal to A squared minus T3 squared. We take the square root of both sides, we end up with T2 is equal to the square root of A2 squared minus T3 squared. Pretty basic Pythagoras triangle. We also know on the other side here, T1 squared plus T3 squared is equal to A1 squared. We have that written out here. Therefore, T3 squared will be equal to A1 squared minus T1 squared. We also know we can calculate L pretty easy because we know Pythagoras rule, Z squared plus X squared equals L squared. Have it written down there. Therefore, L will be equal to the square root of Z squared plus X squared. Fairly basic Pythagoras rules there. Right. Now what you notice up here, we have T2 is equal to this and T2 is equal to this. Right? So that means that must be equal to that because they're both equal to T2. So we can write that down here. Shifting everything across, getting in here. We can write that down. That equals that. If we square both sides, we'll end up with A2 squared minus that side squared. If we multiply out the square on that side, we end up with that. All right? Now here we are minusing T3 squared. Over here we said T3 squared is equal to that. So we can substitute that in for T3 and we get that there. We can multiply out this brackets by the negative there and you get that. Now you might notice in this equation they're both plus T1 squared. So the equation will still become balanced if we minus that off both sides. We end up with this. In the end, we're trying to calculate what T1 is, and it's minus. So what we'll do is, we'll drop that on the other side to get rid of the minus, take both of those back over to the other side there, and we'll end up with 2LT1 equals L squared minus A2 squared plus A1 squared. We can divide both sides by 2L, and you'll end up with the magic T1 we're trying to find out will be equal to this. Now, of course, we can work out A2 squared and A1 squared because we know the length of our arms. We can work out L very easy, like we did before, because of Pythagoras rules there. We know L is equal to the square root of Z squared plus X squared, so we can calculate that out. So what happens is that very easily we can calculate L. Once we can calculate L, we can calculate T1. Once we can calculate T1, we can calculate T2 very easy because we have L and we have T1, so now we can calculate T2. So now we have both T1 and T2. Once of course we have T1 and T2, we can substitute in back into our formulas here, and boom, we know theta 4 and theta 3. We can set our motors and away we go. So to try to keep these videos a bit shorter, in the next video we'll actually write the program to set the motors, and we'll do a bit of error checking, and we'll also work out how to calculate this last motor here.